All right, there we go. All right, good morning, everyone. Welcome to SREcon 2017. Nil and I are here today to talk about TrafficShift, avoiding disasters at scale. So who here, raise your hand, has been involved in an incident where you had no disaster recovery or mitigation strategy? All right, a fair number of you. Glad I'm not alone. All right, so today we want to discuss about how LinkedIn does disaster recovery and how we can avoid or minimize impact to our users when the inevitable does happen. So we're going to walk through how our infrastructure has grown from a single site to a multi-data center active-to-active setup. We shift traffic between those data centers to disasters at scale. All right, so firstly, just a quick overview. We'll talk about LinkedIn's architecture, how it's grown, and what it looks like today. And then we'll go into a deep dive on how we do fabric disaster recovery and what some of the mechanisms we have to do that are. And then we'll conclude with some key takeaways and questions from you guys. All right. So LinkedIn is the largest professional network in the world. We have 467 million members across 200 countries. And for ourselves as a business, but also for our customers, our members, it's extremely important to have high availability all around the world, not just the US, all around the world, to ensure that as engineers, we can keep developing our infrastructure and our products, but also for our customers so they can connect to opportunity. So who are we? Who are Nil and I? So we're on a team called Production SRE at LinkedIn. And the key tenets of Production SRE are to assist in restoring stability during site-critical issues, developing applications to reduce mean time to detect, or MTTD, and mean time to resolve, MTTR, to provide direction around monitoring and also build tools for efficient site issue troubleshooting, correlation, detection. And as this presentation goes on, you'll notice how much the work we've done with TrafficShift fits into those top two tenets listed. All right, so before we start, I just want to deep dive on some terminology that might be useful for everyone. So firstly, a fabric or colo. So this is a LinkedIn data center. We run our own data centers with a full production application stack deployed. A POP or an edge is the entry point into the LinkedIn network. This is where we terminate TCP and SSL connections. Then load test, which is a planned stress test of our data center. So I'm now going to hand it over to Anil to talk about LinkedIn's infrastructure evolution and to talk about fabric disaster recovery. Anil.
Thank you, Michael. Hey all, good morning. Hope you are all having a peaceful on-call today. I jinxed it, didn't I? Well, let's get started. Let's talk about evolution. So everyone knows about evolution, ape to human thing. Let's talk about how LinkedIn's infrastructure evolved starting from 2003. LinkedIn officially launched in 2003. I think probably in Reid Hoffman's bedroom maybe. I don't know. In 2010, until 2010, we were served out of one co-location space in South Bay. So in 2010, we decided and we built a first data center. We were like, oh yeah, we built our first data center, but no backup, nothing. If power went off in that data center, we were like screwed, big time. A banner page would come up saying that LinkedIn will be down for this maintenance thing, we'll be back up. We decided that's not really a good thing, so we built another data center. We started running it in active, passive way. This was just a backup data center. It didn't really serve any purpose until the first data center goes down. Then in 2013, we were like, okay, enough is enough. We are scaling, we are growing big. So we built another data center, active and active. Now we have two active data centers serving well. Until 2014, we were like pretty good. In 2014, that's when we decided it's time to go multi-colo. Then we built 3 data centers, 3-way, active, active, serving really good. Until 2015, we didn't really have any problem. We were serving really well. We started seeing more of APAC growth. In order to address the growth, we built a 4th international data center. Envy active. So we run 4 data centers active. So where are we now? In 2017, we are currently serving LinkedIn out of 4 data centers, 3 domestic ones and 1 international data center. And we have 13 POPs located geographically across the world. We have 1,000 plus API endpoints from our hundreds of microservices. We pushed microservices to the edge. All right, so why do we care about building these data centers? Why do we care about availability? Even if you have like super user experience, super user interface, if your availability is shitty, nobody's give a damn about you. People are not going to come to your site. They're going to be like, hey, that site takes breaks every once in a while. Why should I even bother installing that app? Why should I even visit that site? Availability is very critical for any of the internet applications. So we consider availability pretty seriously because availability with user experience translates to happy users. Happy users translate good business. That's good for us as SREs as well. So our title is aptly named Avoiding Disasters at Scale. So you might be wondering, what are the disasters? Like, what disasters are we considering at this presentation? Like, when I'm talking about disasters, I'm talking about service degradation. So you have this happy service which is running happily, serving users, keeping them happy, and at one point of time, on a Friday evening, when you're about to take off, it just goes all grumpy and dies down. Yeah, users are not happy anymore. Second thing, infrastructure issues. We all know we have been using the biggest cloud network, their services, but they are still not susceptible. Like, they are still susceptible for disasters. They go down once in a while, and you don't really have any control over it. But you have control over one thing, your infrastructure. So please raise a hand if any of you were in this position. Duh, I just pushed the wrong config, brought down the whole site. Yep, human errors. These are very important. We don't really consider this thing like seriously, but yeah, most of the errors, most of the site issues are mainly because of the velocity of the services. Like how many times that we push code. We have been pushing like 3 times a day, 30 times a day, 3,000 times a day. Yep, as and when you push more times a day, issues gonna occur once again. So you gotta factor in your disaster recovery, human errors into your disaster recovery plans as well. All right, the last and the most important one. Data center on fire. Have you guys heard about this thing? Has anyone of you heard that data center went on fire? Oh, great. I haven't really heard. I just put it over there because math says there is a 50% chance. So we at LinkedIn always has one solution, a magic pill for all of these disasters. TrafficShift. We reroute all the users' live traffic from affected data center to the other healthy data centers without any user interruption, like minimal user interruption. End users won't even notice that our data center is on fire until they read it in the next day. So now you probably might be wondering, what the hell is this guy talking about? Hold on a minute. Give me a couple of minutes. I'll try and make it as simple as possible. Maybe kind of like give you an idea on how to implement the same thing at your companies, make your services more recoverable, disaster-free. Before we start diving into how we do TrafficShift, we need to understand the underlying infrastructure, the one that we have, how we structured our LinkedIn's infrastructure. So users requests when it comes to internet. So we have border router, IPVS, ATS. So our TCP connection terminates at IPVS. Then we have ATS. If you guys don't know what ATS is all about, it's an open source web server called Apache Traffic Server. Apache Traffic Server works with that blue box over there. That blue box is our black box. It's the main component I'm going to talk about today. Then it finds the fabric that we have to reroute the users. So the request finds their destination. They're happy. Yay. So let's see how ATS kind of figures out which data center the user's request should be rerouted to. Once the user's request hits the ATS looks into the request header to figure out a cookie, LIDC, cryptographically signed cookie, it kind of finds out if the data DC1 is in the cookie, it redirects that request to the DC1. Then it kind of like, okay, if the cookie is invalid, what's it going to do? It's going to look at the sticky routing service. It's going to ask, like, hey, this user just signed in. Where should I reroute this request to? So sticky routing service gives that answer. It tells us that, okay, DC2, this user belongs to DC2. Stick is all requests to DC2. So the user request moves to DC2. And now let's talk about sticky routing service in a little bit detail. So sticky routing service is just another service at LinkedIn, which basically takes care of assigning users to a particular colo. How it does it? So sticky routing service basically considers a fabric or a data center as just another layer. Inside its little brain, it divides a data center into 100 buckets. This is just a logical abstraction. So a data center is divided into 100 buckets. And each bucket has two states, online and offline. The red ones, probably you're wondering, like red ones are offline, green ones are online. All of LinkedIn's 450 plus million members belong to either one of these buckets. So when a bucket is offline, the user's request that belongs to those buckets will not enter that fabric. They have to find another way, like another data center. How we do it? So first, sticky routing, it basically runs a Hadoop job regularly for all the 450 plus million members, kind of looks at the members' geographical location to the nearest fabric or the data center. Then it considers the capacity of that fabric and assigns these users to that data center. So you can consider it as a simplified version of key value store. Key being the user ID, value being the primary data center and the secondary data center that user belongs to. So if the primary data center is down, then now the user has like secondary data center. So all his requests will be routed to the secondary data center. So what are the advantages of sticky routing? So since we started with the inception of sticky routing, we have seen very less amount of latency because users are always routed to the nearest fabric, to geographically located to them. Second thing, we store data only where it's necessary. That's a good thing, right? More data equals more chaos. It provides us precise control over how we capacity control the fabrics. See, if my manager comes up to me and says, hey, Anil, I don't want 10,000 QPS to be routed to this data center, take it off. I can precisely take off 10,000 QPS out of that data center and put it elsewhere. It's good. It gives you precise control. So what is TrafficShift? So rerouting users' requests from one particular data center to the other data centers, that's what we call TrafficShift at LinkedIn. It's the term that we use. So when do we do TrafficShift at LinkedIn? Pretty much every day, like twice in a day sometimes. To impact mitigation. Whenever you have like microservices architecture with over 100, 200, 300 plus services, failing out or failing over just a single service or single microservice from one fabric to another fabric is not that easy. So you're going to introduce cross-colo latency, you're going to introduce other n number of problems. So filling out the whole data center, that's the simple solution. For that, you need to have the underlying infrastructure. It has to support that. So whenever we have any impact at LinkedIn, consider a data tier goes down in one data center, we're going to right away fail out of that data center. This gives engineers an ample amount of time as well to what's going on because they don't have to worry about users being served 5xx or any other n number of errors. Plan maintenance. As you all know, maintenance, we can't really get rid of maintenance. So some of it is third-party maintenance, some of it is in-house maintenance. It's going to take time. So whenever we have planned maintenance for security or safety purpose, we just fail out of the data center. Stress test. As you all might know now, rerouting users gives us precise control. Now we can use the same underlying TrafficShift architecture to stress test individual colos. So let's see what disaster scenario looks like at LinkedIn. Let's say we have 4 data centers, US East, US West, US Central, and APAC, the 4th one. So for some reason, somebody pulled a plug out of US East. There's no power to US East. Boom. APAC, yeah, it just went on somehow. I don't know why. Now, if we just leave it at that state, 50% of the traffic is routed to that data center. We are losing 50% of the traffic. That means so much of attrition from our users because, trust me, users are fickle-minded like me. I'm a user. Traffic stops being served. Now, when I say that traffic shift, I'll mark US East data centers and APAC data center as offline using my sticky routing service. I'll take down the buckets in those fabrics as offline. The traffic stops flowing to them and redirected to US West and US Central. Now we are serving all of the 100% traffic out of 2 data centers. That's our disaster scenario. That's what we load test or stress test for all the time at LinkedIn. 2 of our data centers should be online, and we assume that they will be online, even though 2 goes down, and we'll be still up and running without any interruption to users. So let's look at TrafficShift architecture, how we kind of designed the architecture for this TrafficShift toolset. TrafficShift is basically 2 services, a web application in the front end and a back-end worker processes. We use Couchbase as our persistent store, and we leverage Salt Stack heavily in order to communicate with the data center of fabrics. So it works in tandem with the sticky routing service. Suppose, let's say I want to offline the US East data center. So either production SRE or any site ops engineer who has, like, you can precisely control the authorization. You don't want to give the skill switch to everyone in your team. So that person's going to go to the web application. He can precisely say that, hey, I want to offline this data center completely, 50%, 20%, 20%. It creates a plan. The backend worker process reads that, kind of like works out what has to be done. It communicates to the salt master in that fabric, whichever the data center that you want to take down. Then the salt works, talks to sticky routing service and instructs it to perform the task. Hey, dude, just turn it off. Like, just turn off 10 buckets. Here, in this example, 2 buckets. So sticky routing service will mark those 2 buckets as red. Now, we all know when the request comes in, if this data center and that particular bucket, if the user belongs to that particular bucket, the ATS will kind of gets to know that, hey, this bucket is offline. I got to find the secondary data center for this user and reroute those requests to the secondary data center. So the secondary data center would be one among them, the domestic data centers, the 50% load ones. That's how we do traffic shifts at LinkedIn. Let's talk about load testing. So you might be wondering, load testing is just a term that we use at LinkedIn, which is basically a planned stress test of a fabric or a colo. So people do this all the time in other companies as well, but they consider it as a disaster recovery process, and they test it once in 6 months, once in 3 months, sometimes once in a year. We do 3 times a week. We stress test our colos 3 times a week during peak hour traffic. So, and you guys might be wondering, like every one of you might be wondering, thinking that, why do you guys take such a risk of stress testing a fabric at a peak hour traffic? Because everything is precisely controlled and everything is run in a precisely controlled manner. So even if there is a slightest alert that goes on, the traffic shift tool has its automated engine built looking for alerts. If an alert goes on in a particular zone, kind of rebalances the traffic, thereby averting the disaster. So what do we gain by doing this load test? We have a fixed SLA for all of the service owners who face any difficulty or whose services broke down during the load test. So the fixed SLA is taken pretty seriously. All of these issues should be addressed prioritarily. Like it gains the highest priority. So let's see how we load test. A simple example to show you guys. So there's US West, and we are testing target data center. There's US East and US West. I have to redirect traffic from US East to US West. So from US West, I'll mark offline some of the buckets, and from US East, I'll mark some of the buckets. All of this traffic is now rerouted to target data center. We'll stress test it approximately up to 50% because that's our disaster recovery scenario. We'll hold on at that level for a couple of hours maybe, and then we will rebalance. So every load test will have its own automated reports that will be sent out to a particular mailing list. So there are a lot of benefits. So the main ones, as we have been doing load tests, we have gained pretty good amount of information regarding the capacity of our data centers. So we know, if you tell me the day, day and the hour, I can pretty much tell how much QPS or traffic, our data center can serve at that point of time. So capacity planning has been very easy because of our load test. And then we leverage production traffic to stress test our services. So service owners, they need not do anything at that point of time. They'll just come by, they can look at the graphs for that particular time, and they can figure out, how their services behave looking at the graphs during the load time. They know from the reports that we sent, they know what was the QPS that actually that Fabric received, and now they know like, my services received this much, I think I should capacity uplift my services, or I have some machines which are lying freely. I can pretty much take down some of the servers down and reclaim those hardware. Identify bugs in production. This is the most important. Some of the stress-related, like performance-related bugs doesn't surface during high test scenario. So whenever we load test, some of this performance bug arises. But as we are doing a controlled manner load test or stress test, we can avoid the crisis and figure out what the bug is, fix it. Confidence in disaster recovery, last but not least. So as we have been doing this for like past couple of years, we have gained enough confidence in our disaster recovery scenario. So we are now pretty confident that no matter if a data center goes down at any point of time, we are still up and running, keeping our users happy all the time. Last year, we added a kill switch. It's a kill switch. So this kill switch came, was given a notice because we figured out in a couple of situations in the past. So the main impact that we used to have was we were not failing out pretty fast from a data center. Our users were still experiencing more failures, more error rates. So this kill switch basically drains all of the Fabric and the POP traffic in less than 10 minutes with minimal user impact because it again utilizes the TrafficShift architecture. So kill switch is now an easy switch. Now I hand over my mic to Michael for the key takeaways.
Thanks, Anil. All right, so from this rather large exercise that's taken a number of years for us to develop, what have our takeaways been? So firstly, as SREs, we try and design our architecture to be as highly available and as highly resilient as possible. But in all reality, disasters will happen. So for us, we assume that there will be a disaster. So we think about, what our infrastructure looks like to facilitate disaster recovery, and then on top of that, to go and automate disaster recovery. When we first started this, this was actually an extremely manual process. It was a Python script, somewhat error-prone. We've actually spent a lot of time to make that better and automate it for all of us to make our lives better. Secondly, stress test. So as Anil said, the velocity of change within LinkedIn is really high. We've got a couple of hundred microservices, lots of APIs. So continuously validating our disaster recovery and our capacity is extremely important for us. And then finally, as I said earlier, automation is really important. So automating our disaster recovery is as important as automating other parts of our job. We've spent a lot of time making this better and basically automating the end-to-end process for traffic shifting for disaster, but also for load testing. All right, so that concludes our part of the presentation. I'd now like to hand it over to the audience for questions. There's a microphone in the middle. If you could use that, please.
Thanks for the presentation. I had two questions. The first, based on the first, second or third slide that you showed, it looked like on the edge nodes you were using the your sticky session service, and then later on you were showing that there was inner data center traffic. Do you have two versions of that service, or does it run independently on each of the POPs?
No, so like we have data center to data center traffic for replication, not for online APIs. So the sticky routing service is only concerned with traffic coming in from the outside.
Okay, yeah, and that was my next question. Was a follow up would be how do you handle kind of the replication between the data centers for like user sessions and things that you need to kind of move off of once you route someone off?
So it somewhat depends on the service, but basically we expect all data replication to be done in real time. You know, if the data hasn't caught up within X amount of seconds, I don't know what the SLA is off the top of my head, we consider that an incident because we lose our disaster recovery strategy. So we expect to keep data in sync between our colos all the time.
Thank you.
Welcome.
You mentioned that there's a user interface for manually shifting traffic around, but I imagine that there's automatic intelligence as well.
Yeah.
For
I'll let Nil take that one.
For the automatic intelligence, how do you prevent situations where users are flapping back and forth between fabrics, which could lead to poor user experience?
So the automatic one is basically it comes into picture when we are load testing or stress testing. So the other one is the manual one. So we don't really let the tool itself automatically decide if it has to move the traffic. So during stress test, all it does is basically rebalance the traffic, let the user go back to his home thing, because during stress test, all the 4 colos or all the 4 data centers will still be online. It's just that we'll rebalance based on the alerts. So that prevents us from users hopping around the data centers.
Oh, I see. OK. Thanks.
Hi, guys. Thanks for the talk. This question's for Anil.
Yeah.
It's kind of related to what the first questioner asked.
Yeah.
The sticky routing service, does that run in your edge POPs or in the data centers?
It runs in the data center.
But I thought it made decisions at the edge.
ATS makes the decisions at the edge. ATS has a plugin system. Sticky routing has a plugin inside the ATS. That plugin contacts it's just a REST interface. So
yeah, so the sticky routing API runs in the data center, but the edges talk to that data center. In the case that we lose connectivity between the edge and the fabric, sticky routing just keeps the steady state.
OK. Cool, that makes sense.
Yeah, and like if we lost connectivity between the edge and the fabric, we'd be moving traffic out of that data path anyway to prevent problems.
All right, thank you.
That, I think, was the last question. If you want to come up after, we're happy to take your question. All right, we've got time.
Yeah, I was just curious. So you split each data center into 100 buckets of capacity. So
Yes.
do you have like homogeneous capacity in each of your data centers? Like, can they all handle approximately the same amount of traffic, or is that just to allow for like hashing of users across, but it's not actually?
Yeah, so that's a good question. So using our Hadoop job, which sort of takes the geographic inputs and the capacity inputs, that job basically knows how much hardware we have in each data center, and we sort of make an abstraction on top of that.
Right, but a bucket in US East is not equivalent in capacity to one bucket in US West. It's just
without giving too much away, all of the US is the same, basically.
Okay.
When you start looking and building data centers in other markets, you don't need the same amount of capacity.
Thank you.
All right, thank you very much, everyone. Enjoy the rest of SREcon. Thank you.